Let's introduce friction. Of course, we've been ignoring it up till now because we've been keeping our models of the world very simple. But the world has friction, and our models have to become more advanced so we can account for that. First, let's take a little review on normal force. Let's say I've got a table here, and I push down with the small force F1. The table pushes back with a small force. We call that the normal force. If instead I lean on the table a little harder, I push down with the force F2, the table pushes back with a slightly larger normal force. And this continues until I push so hard the table breaks and I fall through the table. The normal force reacts to whatever force is pushing down to support it. Maybe that's a hard thing to grasp. But think about what's happening at the molecular level. If we look at the atoms that make up the table, each one is in a bond with the atom next to it. And those bonds are like springs. They want to be in their equilibrium position. If we stretch them, they will apply a force to try to get back to their equilibrium position. So if we put something on this table, or if we press on it in some way, those springs stretch, those bonds stretch. They want to be in their equilibrium position, and they produce a normal force up on whatever it is that deformed them down. And if we push harder and those springs get stretched even more, the normal force is bigger and reacts to that. So this is sort of a crude model of what's happening at the atomic level and why that normal force reacts and becomes larger as we push harder on the table. Static friction is similar to normal force in that it reacts and can change. Let's start with a simple situation. We have a flat surface with a book sitting on top of it. There's a normal force pushing up because the weight of gravity is pulling down, and the normal force is supporting the book. But there are no horizontal forces. There's no friction force, because if there was, then the book would have to be moving in that direction. If there was some net force in the horizontal direction, we know that net force equals acceleration. The book would have to be moving in that direction. And it's not moving, it's stationary. So we know there's no horizontal forces. So in this case, we have no friction force. Now let's say I tilt the table just a little bit. So my book is at rest, and it's still stationary. It's not sliding down the table, it's still stationary. I have a normal force. I have the weight towards the center of the earth, and I can break that up and say that it has a component of that weight down the incline, and there's a component perpendicular or normal to the incline. I'll call that weight sub x and weight sub y. So there's some force down the incline. Some part of the gravitational force is down the incline. But my book's not going that way. I know that there has to be a friction force up the incline. And I'm being very careful to use the subscript S for static friction. Static means not moving. These two surfaces are not moving in relation to one another. The book and the table are static. There's no motion between them. We'll get to kinetic friction in a minute. Kinetic friction means there's motion, there's sliding between the two surfaces. I went from case 1 with no friction, case 2 with a small amount of friction, and if I increase my angle a little bit, If I increase the angle a little bit from the table, and my book is still at rest, it's not sliding on the table, I've increased the weight of gravity in the downward direction along the incline of the table, that's W sub x. So I must have a friction force that's even larger than before, that's equal to the weight of gravity going down, so my book's not moving. I went from no friction force in case 1 to a small static friction force in case 2 to a large static friction force in case 3. And if I increase the angle even more, I will eventually get to the point where the weight in the x direction is greater than the maximum static friction force, and the book slides down the table. So the static friction force is somewhat similar to the normal force. It reacts. It starts off at 0, and then as we tilt the table, it becomes larger and larger until it hits some maximum value. It can't get any bigger than that, and that's its maximum value, and then it gives up and the object starts to slide. That's static friction. Now let's take a look at what happens once this book starts to slide. In this case, we always know what the friction is. It doesn't change. Once something starts to slide, once we have kinetic friction, we can calculate it. It doesn't matter if it's sliding at 1 meter per second or 100 meters per second. We can calculate it. We can figure out what it is. So kinetic friction is fairly simple. It's proportional to the normal force. It's equal to a constant, mu sub k, times the normal force. That's our kinetic friction, never changes. We always can figure out what the kinetic friction force is equal to. Static friction is a little more complicated, as we've just talked about. It changes, so we never know exactly what it is from a formula like this for friction. We have to figure it out from other information in the problem. If we knew the angle of the book and the mass of the book, we could figure out that static friction force had to be equal to the weight in the x direction in this previous example I just drew. And so we could figure out what it was. But we can't figure it out from a formula like this like we have for kinetic friction. But what we can figure out is the maximum. And that's equal to mu sub s times the normal force. And these mu's, those are the coefficients of friction. And those depend on the surfaces involved. Some surfaces are very slick and slippery and don't have very much friction. They would have a low friction coefficient. Some are very rough and provide a lot of friction. Those would have a high friction coefficient. The kinetic friction coefficient is typically less than the static friction coefficient. And this is a unitless quantity, typically less than 1. For our purposes, it's always going to be less than 1. But they do have some materials that have a coefficient of friction greater than 1, like race car tires. The tires on race cars are actually very sticky. So you press them down on the ground and you try to lift them up, and they stick to the ground a little bit. So when you try to slide them, they have a coefficient of friction that's greater than 1 because of the sticky quality that they have. But for our purposes, our objects are rigid and they're just sliding across one another, and our coefficients of friction will always be less than 1. There's one more point I'd like to make here. Let's take another example of a block on a horizontal surface, and let's pull on that block with some applied force. So when that applied force is equal to 0, the friction force is equal to 0. If we don't pull on the block, there's no friction force. It's a horizontal surface. If we pull with the force of 1 Newton and the block doesn't move, then the friction force has to be 1 Newton in the other direction. And we keep increasing the value of the applied force, and the friction force keeps increasing until it hits some maximum value. That's the maximum static friction. And then we pull a little harder, but the friction force can't increase, so the block breaks free and slides to the right. And now we are in kinetic friction. The kinetic friction force is typically less than the maximum static friction force. So this section is static friction. And this section is kinetic friction. And I'll go ahead and label this as F, kinetic. This is one reason we have anti-lock brakes on our cars. What happens when the wheel is turning and you're braking? You're actually in what we call static friction mode, because as the wheel rotates, the tire does not slide on the roadway. That's static friction. The two surfaces are not moving with respect to one another. But if you slam on your brakes in an older car, new cars have anti-lock brakes, but if you slam on your brakes in an older car, you'll lock your wheels and you'll go into a skid. And that's kinetic friction. There's sliding, there's motion between your tire and the road. And you'll see from this chart I just drew that that's typically a lower coefficient of friction than your maximum static friction. So one of the reasons we use anti-lock brakes is that it's possible you could actually stop your car in a shorter distance if you do not let your brakes lock up and go into a skid. If you sort of pump the brakes on and off very fast, that's a computer in your car does that for you. You just slam on the brakes in a new car, and the computer adjusts the brake such that the wheels don't lock and go into a skid. And you are always in static friction, and your car may come to rest in a shorter distance. But the main reason we use anti-lock brakes is that if your wheels are turning, you still have steering control over your car. If you go into a skid, it doesn't matter what direction you turn your wheels, your car is going to go whatever direction it wants to.